In this video, I will talk about regression specification in Stata. Before you watch this video, please make sure that you have watched my other video called Regression Specification. So let's go ahead and get started. I have opened up the program here and I have downloaded the two data files. I have told Stata where the data files are located, and then I have executed the program, and this is the output. So in this presentation, I will talk about reset, and then I will talk about proxy variables, and then measurement error in the dependent and independent variables. So let's go ahead and get started. First, let's talk about reset. Reset is regression error specification test, and it includes squares and cubes of the fitted values in the regression model and tests for joint coefficient significance. So here's the data file that we're going to be using, wage1.dta. And what I will be doing is running a regression model of wage on education, experience, and tenure. So what I want to know is if this model is correctly specified. So once the model is estimated, what we will do is we will predict the fitted values. I will call this y hat, and then I will generate a variable called y hat squared. So I will take the y hat above and square it, and y hat cube, I will take the y hat and cube it. So in the reset, we would be testing for joint significance of the coefficients on y hat squared and y hat cube. So we would be running the same regression that we have here above, but we would also include this y hat squared and y hat cube. So the null hypothesis here is that the model is well specified, and the alternative is that the model is misspecified. And how we will do this is with an f-test. So we're going to be testing whether the coefficients on y hat squared and y hat cube are zero. So the coefficients here, whether they're zero. So here's how the results look like. So this is the regression model of wage. So we see these are the coefficients. We actually see that many of them are significant at the 5%. This experience coefficient of experience is significant at the 10%. So again, we're getting the predicted values and we are squaring, cubing them, and then we are putting them back in the regression. So again, these fitted values are now here to possibly test whether there are any high level square terms or interactions of variables. So we would be noticing here that these two coefficients, actually, if we look at them, one of them is actually significant and the other one is not significant. So the correct test would be an f-test, and we would be testing whether or not these coefficients are jointly significant from zero. And this is the f-test statistic, and the probability, the p-value is less than 0.05, therefore the model is misspecified. So what this tells us is that if these coefficients are significantly different from zero, these squared and cubes of the fitted values actually significantly contribute to this model. So basically, we need to keep looking for alternative specifications. So now I will repeat exactly the same thing as I did here, basically 3 more times. And here I would have a regression model of log of wage. So everything is the same except I have moved to log of wage instead of wage. So again, predicting the fitted value, generating the squares, the cubes, putting them into this regression and testing whether or not these coefficients are jointly significantly different from zero. Then I will generate education squared and tenure squared for a couple of the variables. And so now I will also test the regression where I have the square terms here, not just the straight terms, but also the square terms. I will repeat the same procedure for the reset test, and final model would be the regression of log wage, including the square term. So I have switched here to log of wage, and there's also square terms. So the same thing, getting the predicted values, getting the squares and cubes, putting them in the regression, and testing whether these coefficients are jointly significantly different from zero. So let's see what the results are. So the first model told us it is misspecified. So we need to keep looking. The second model, when I switched to log of wage, these are the coefficients of the model, getting the predicted values from here, the squares and the cubes, putting them in the regression. We're seeing that these now are this one is significantly different from zero. This one is also significantly different from zero. And if we do the joint test for significance, we again see that the p-value is less than 0.05. So therefore, these two coefficients are significantly different from zero. This means that the fitted values, the squares and cubes of them, are picking up information from the model. So again, we have a misspecified model. So keep trying. Now with the model, we have now the square terms here. We estimate the model, get the predicted value square, cube them, put them back into the regression, and again, estimate everything and then test for these two coefficients here if they're jointly significantly different from zero. And again, this f statistic and the p-value are showing that it's less than 0.05. Therefore, again, we have a misspecified model. So even though these two coefficients individually are not significantly different from zero, jointly using an f-test, they are significantly different from zero. And then the final model is where we switching to log of wage, and then we have also the square terms of the independent variables here. So again, these are the coefficients calculating the squared and cube values. You put them back into the model here and you estimate the model. So now I'm looking at the coefficients of y hat squared and y hat cube. And these are the coefficients that we have here. And I'm looking at the p-values. So these coefficients are not significantly different from zero using individual t-test. And if we actually look at the f-test, we have that they're also not jointly significantly different from zero. So we finally found the correctly specified model. So this is what the reset test did. We experimented with 4 different models, and since the first ones told us that actually the models are misspecified, we kept including squares, we kept moving to logs and so forth until we finally found a specification that is correctly specified. And we used the reset test for that. Okay, so next we will discuss proxy variables. So here, basically what we are going to use a proxy variable for is if we're missing a variable from the data set, but we really need to include it in the model. Otherwise, we're going to have an omitted variable bias. So what is going to happen is if we don't have this omitted variable, well, the second best solution would be to put the proxy variable in it. So this is what we're going to be doing here. So we're going to read in the data wage2.dta. So now one of the issues here is that we're going to be using IQ as proxy for ability, but the data set does not have ability. So just for purposes of teaching and to show you what actually could happen if we actually had that variable, but we omitted it, I'm going to generate a fake variable. So this is how that's happening. So we will set 935 observations. This is how many we have in the data set. We're setting a seed number of 0 and then generating R, which is R normal, coming from the standard normal distribution with a mean of 0 and variance of 1. And then we would list this R, randomly generated variable, the first 10 observations. So this is what I have done here. And this is how this variable looks like. So this is a standard normal variable. So what we know about the standard normal distribution is that 95% of the observations would be between minus 1.96 and 1.96, and that's what we see here. So now I would generate a fake ability variable by using this equation. So this would be equal to ability 1 would be equal to 5 plus 10 times the IQ variable plus this standard normal variable. So if you look at this, this looks like a regression model, only that I made up these numbers, 5 and 10. And so I now generated the variable ability 1, and then I'm rounding this ability 1 to a whole number, and I'm calling this variable ability. So now here's I have the new data set, and I can summarize it and list the first 5 observations of this new data set that I created. So these are the summary statistics. So I have the mean for wage, education, ability, and IQ. That's how my ability variable would look like. And these are the first 5 observations of it. So let's suppose that we have a variable ability that looks like that. So now, again, no one would do this in real life to generate a fake variable on purpose. So but for teaching purposes, I wanted to show you what it would mean if we did have that variable, but we on purpose did not include it in the model. So now let's estimate different models. The first model that we would be estimating here is the true model that has education and ability here. So we would regress wage on education and ability, and we would do this by doing reg, wage, education, ability, and we would be generating this beta 2 coefficient right here on ability. So this would be underscore B, the coefficient for ability, and we will be displaying beta 2. So this is how the true model looks like between wage, education, and ability. And so this is what we see here. So I would like to note the magnitude of the coefficient on education. So this is 42. So this is basically, if that was our true model, this would be an unbiased coefficient on education. I also want to note that the coefficient on ability happened to be 0.51. But again, I'm focusing on this coefficient with the magnitude of 42, which is unbiased. And here I would generate beta 2, which is underscore B. This means pick up the coefficient on the ability variable. And when we are displaying beta 2, we would see that this is that coefficient here, the coefficient on ability. I'm just storing this in memory as beta 2. Okay, so what we're going to do next is we will calculate the model with the omitted variable ability. So the coefficient on education would be biased. So I will do here regression of wage on education. You see how ability is missing. So if we don't have ability, we actually didn't have ability in that data set. That was the original data set when we don't have it. Here is the result that we're going to have. So notice now that the coefficient on education is 60. So that coefficient before was 42. So basically this coefficient is biased because it's trying to pick up some of the effect of ability on wage through the relationship between ability and education. So this is how this coefficient is biased. It's equal to the original coefficient 42 plus the bias due to the fact that we don't have ability in the equation. Well, this is really bad. That coefficient is biased, so we don't want to have this situation. So what can we do? Well, one solution, the second best solution is if we don't have ability, is to use IQ, which is proxy for the omitted variable ability. And now I'll have the model for the ability on IQ. And here would be ability regressed on IQ. And this will be the model here. I have ability regressed on IQ. And these would be the coefficients that we have here. So notice something interesting. That coefficient is very close to 10, and this coefficient is very close to 5. And the reason for that is, if you remember how I actually generated that ability variable, is I gave it the equation 5 plus 10 times IQ, plus you give me an error term that came from a standard normal distribution. So actually, once I run the regression of ability on IQ, I get back the same coefficients that I originally used to create that variable. So anyway, this is not surprising at all. So what we will do here is we would generate delta 2, and delta 2 we would pick up the coefficient on IQ and we would be displaying it, and that will be that coefficient of 10 here on IQ. So now let's run a model with IQ as proxy for ability. So here we would have a regression of wage on education and IQ, and we would be displaying the coefficient on IQ. So here we have, this is the model of wage regressed on education and IQ, and these are the results. So one of the best things about having actually a proxy here for ability, and in this case that's our IQ, is that this coefficient on education is 42. So notice that that's very similar to the coefficient that we had here in the original model, in the true model. So including here a proxy variable, we actually do not have this coefficient biased anymore, like it was 60, it was biased before. But now we have the unbiased coefficient. So this is really great news. Another thing to notice is the coefficient on IQ. So if we're displaying this coefficient on IQ, that's that coefficient. But how we also can calculate it is if we multiply that coefficient beta 2, and this coefficient beta 2 is the coefficient on ability in the true model, times delta 2. Delta 2, if you recall, is the coefficient of IQ on ability. So that was delta 2 here. So if we multiply these two coefficients, if you scroll back up, this beta 2 was equal to this beta 2 coefficient was equal to 0.51. So here. And the delta coefficient here, the delta 2 coefficient here was equal to 10. So right here was equal to 10. So actually what we have here is that this coefficient here is a multiple of the original coefficient of ability on wage times the coefficient of how ability relates to IQ, which was basically 10. And so that's how we received this coefficient. So again, as a conclusion, when we use a proxy here for ability, so IQ is proxy for ability. The nice thing is that we have unbiased coefficient on education, and this coefficient here is a multiple of these two coefficients that we had before. Okay, the final thing that we would be discussing here would be measurement error. So we would be reading back wage one data set, and here on purpose, I would be generating mismeasured variables. So here, what I would be doing with the wage variable, I would be rounding up to the next $5. So I would be generating wage mismeasured equals 5 if wage is positive. Then I'll start replacing it. If the wage is greater than 5, I'll put it at 10. If it's greater than 10, I'll put it at 15, and so on. And so basically what I'm doing is I'm rounding up to the next $5 with this code for wage. And I will on purpose generate a mismeasured variable, experience mismeasured, which is rounded up to the next 10 years. So if experience is positive, I'll put it equal to 10. If it's greater than 10, I'll put it at 20. If it's greater than 20, I'll put it equal to 30, and so on. And so now let's list all these variables, the original ones and the mismeasured ones, and let's summarize them. So this is how the data set looks like. So these were the original variables, the original variable wage, and that's the values. And here is a mismeasured variable that I created. So anything went up to the next $5. So if it was 6, it became 10. It was 11.25, became 15. And if it was this number, it went up to 20. So this is a mismeasured variable. For experience, is rounded up to the next round 10 years of experience, or 20 or 30. So 2 got rounded up to 10, 22 got rounded up to 30, and so forth. So again, if you have the true variables, you would definitely not do this on purpose. I just wanted for teaching purposes to illustrate what's happening. But very often we have data like that. Either people report it like that, misreport it, they boost up a little bit their wage and experience, or it's just recorded as intervals. So we just truly do not know the correct values for the original variables. So I also wanted to summarize the variable wage and the mismeasured variable wage, and the experience and the mismeasured variable experience. So now let's estimate several different models. The first model would be model that has no measurement error. So here I would have regression of wage on education, experience, and tenure. So I'm using the original variables here. And so again, there's no measurement error here. What I would like to notice here is that we actually have a coefficient here on experience, which is 0.022. And this coefficient is significant at the 10% level, not at the 5, but at the 10% level. So now what would happen if we actually have a mismeasured dependent variable wage M? So here if I have the regression of the mismeasured dependent variable on the independent variables, what would happen here is the following. We would have basically very similar coefficients that we have here. But some of the coefficients, they're not going to be biased, but some of the coefficients like this one would lose significance if we have a mismeasured dependent variable. Now, what would happen now if we have a mismeasured independent variable? So here is, instead of experience, I have the experience mismeasured. So what would happen here is that this coefficient here would be less than the 0.22 coefficient that we saw in the true model. And then we are seeing actually the p-value is greater than 0.05. So actually, and greater than 0.1. So actually what happened is that this coefficient actually lost significance. So what we're seeing in this coefficient here is what we called attenuation bias. So basically we have a coefficient that is biased towards 0 and became insignificant. So again, there are much more serious consequences for if the independent variable is mismeasured, because we would have attenuation bias, than if the dependent variable was mismeasured. Okay, thank you for watching.